Hi, I'm Jin Wei. Today I'll be talking about PMThreads. It is a user space runtime that provides data persistence for log-based parallel applications. It's a joint work with Lukai, Andrew Winger, and Miguel. So let's first get to know persistent memory. Persistent memory is a new kind of memory that provides disk-like data persistence, as well as DRAM-like memory performance, and meanwhile it is better addressable. So these novel features of persistent memory makes it possible for us to manipulate persistent data via load store instructions. However, it's not easy to use persistent memory correctly. As shown in the picture, there are typically multiple levels of CPU caches between the CPU and the main memory. And the data movement between CPU and the main memory is mostly controlled by cache coherence protocol, which is typically a black box to user programs. And because a persistent write only takes effect after it reaches the persistent domain, so we have to use explicit cache line flushing operations to enforce such data durability. And this typically introduces significant CPU stalls. And in addition to data durability, we might need to maintain the data consistency for non-volatile memory to ensure correct failure recovery. Let's look at a simple example where we got two accounts X and Y, and account X is transferring 50 pounds to Y. When we cannot apply modifications to them atomically, and a power failure occurred, we might leave the non-volatile memory in an inconsistent state, and we cannot make use of the persistent data anymore. So it's important to provide the user programs with a programming interface that could guarantee a sequence of memory stores to be atomically presented in the non-volatile memory with respect to any potential power failures. And most of existing solutions using logging to enforce such kind of failure atomicity. As shown in the example, a logging-based solution will firstly construct the persistent log entries for X and Y before we making any changes to them. And thus, anytime a power failure occurs, we can always recover the persistent memory to a consistent state with the help of the log. With undo logging, the old value of the target data is firstly logged before touching them, and so that we could perform in-place updates to NVM. And the main drawback of undo logging is that it incurs ordering overhead in each individual write, as we have to persist the log entries before touching the target locations. Whereas with redo logging, we do not perform in-place updates, and instead we write new values to the log. And as a result, it introduces reduced ordering overhead compared with the undo logging. But note that we have to redirect all the read operations to the log to obtain the latest value. And this can be expensive for read-intensive applications. Well, instead of using logging, PMthreads enforce failure atomicity with a novel dual copy scheme. Firstly, the PMthreads leverage DRAM as a shadow memory to buffer updates to the persistent memory. Then the PMthreads runtime will enforce quiescent points to occur at the timed intervals. At a quiescent point, the buffered contents in the DRAM will be written back to their corresponding home locations in NVM. And to support failure atomic updates, the PMthreads maintains dual persistent copies for each persistent page, which are respectively named as the working copy and the consistent copy. And each time we modify the persistent data, we'll only touch the working copy, that is the NVM copy with the dashed outline as you would see in the picture. And we leave the consistent copy as a backup page to support correct failure recovery. And having successfully made changes to the working copy, there will be a committing operation that will switch the rows between the working copy and the consistent copy. And then we will enter next execution interval. Just like the previous one, we will firstly buffering updates in DRAM, and then writing back to the new working copy this time. And finally, the committing operation. And if a system crash occurred, we could roll back the non-volatile data to its latest correct state that's stored in the consistent copies. Okay, next I will detail the implementation of PMthreads in 3 aspects. Let's start with the memory access tracking. And to manage the data movement from the DRAM buffer to the NVM, we need to identify the dirty pages in the DRAM buffer. We investigate both hardware and software-based solutions to track the memory access. With the hardware method, we'll firstly set access permission of the DRAM buffer as read-only, such that any subsequent write access to the DRAM buffer will trigger page protection fault. And our PMthreads runtime will handle such access violation and keep track of the page that's being touched. With the software-based memory access tracking, a compiler path is used to inject a function call to the PMthreads runtime before each individual memory store instruction. We observe that excessive TLB misses incurred by the hardware tracking method makes it less efficient than the software one in our work. And regarding the Quiescent state enforcement, it is basically to ensure that we could capture consistent DRAM state to NVM for data persistence. And PMthreads requires persistent stores to be issued within lock-protected critical sections. And the global Quiescent state could be reached when there is no thread that holds a lock to the persistent data. To enforce such kind of global Quiescent state, the PMthreads runtime carefully intercepts the lock and unlock operations in the PMthread library, and then instructs the locally Quiescent thread to wait on a barrier to reach a global Quiescent state at timed intervals. Next, I'll talk about the failure atomic version management. And before that, let's take a moment to look back over the dual copy scheme. It performs in-place updates to the working copy during the writing back phase, and atomically switches rows between the 2 copies to make the newly updated NVM cache become the next consistent state. However, if we were to modify multiple pages at the same time, merely having the row switching procedure within an individual dual copy pair to be atomic is not enough to enforce failure atomicity for the whole persistent memory. To solve this problem, we propose a versioning-based solution to enable failure atomic row switching among multiple dual copy persistent pages. So we firstly set up a global version number in non-volatile memory and attach each persistent page with a local version number. All of these versions are initialized at 0 firstly. The PMthreads runtime will identify consistent copies through comparing the version numbers. And more specifically, the persistent page with its local version greater than the global version will be judged as inconsistent. And if both local versions are smaller or equal to the global version, the larger one will be the latest consistent version. Let's have a look at the example. Currently we are in T0 and the working copies of P0 and P3 are modified. And we set their version number as 1, which is 1 step forward from the global version. Note that currently the global version number is 00. So according to the consistent copy criteria that we mentioned before, the status of the working copies here are still inconsistent. And right after we increment the global version number, the working copies will become consistent copies. In other words, we have managed to make row switching in multiple dual copy pairs to take effects atomically. And now we enter next interval, and this time we are touching pair 0 and pair 1, and the latest version will be 2, but it is still inconsistent as the global version number remains as 1. And after we increment the global version, version 2 will become the latest consistent version. And if system crashed before we successfully written back the whole right side, the recovery process could safely discard the inconsistent copies while comparing the local versions with the retained global version number. And otherwise, we could safely increment the latest consistent version. Okay, the last part of this talk is a quick view of the evaluation results. The experiments were conducted on a 20-core Linux machine, and as real NVM device was not available, we emulated NVM device while injecting actual latencies to the cache line flashing operations. So firstly, we evaluate PMthreads over 14 applications from the Parsec and Phoenix benchmarking suites. We choose pthread as the ideal baseline, which does not provide any data persistence support. It is purely running on DRAM. And we compare PMthreads against Atlas and as well as MVthreads, where Atlas use word-level undo logging to enforce data persistence, and MVthreads is using page-level redo logging. Besides, the PMthreads P tracks memory access using hardware page protection faults, and the PMthreads I is a variation that monitors memory writes using the compiler instrumentation. We measure the performance slowdown to pthread due to providing the data persistence, and observed that PMthreads I and PMthreads P increase the smallest slowdown in Parsec and Phoenix, respectively. And in the stress test, we measured the throughput achieved by all the evaluated systems on two log-based concurrent data structures, with the workloads containing varied percentage of put operations. Where PMthread 0 is a variation that only performs the necessary pthread interceptions, but does not enforce data durability for persistent memory writes. The figures of PMthread 0 demonstrate that the interception overhead of PMthreads is not significant. Considering scalability, both PMthreads P and PMthreads I outperformed the other systems with data persistence support. One exception is in the thread test results over the linked list with less contented workloads, where Mnemosiny, a logging-based durable transaction system, achieved better performance. And we also investigate the performance of PMthreads with varied Quiescent enforcement time intervals on Memcached, which is an object querying system that caches key-value pairs in main memory to boost the web service performance. We replaced the malloc in Memcached with NVmalloc to make it allocate dynamic memory from the persistent heap managed by the PMthreads runtime. The results demonstrate that PMthreads is capable of enforcing Quiescent points to occur at expected time intervals. And meanwhile, with increased interval, the PMthreads generates fewer interventions and moving more data at each Quiescent point. Additionally, we collect both the volume of data written to the DRAM, namely the volatile writes in the figure, and the volume of writes to NVM that is named as the durable writes. The results show that PMthreads significantly reduce the writes to NVM through buffering persistent writes, leveraging the DRAM-side shadow memory. We also measure the overhead of PMthreads barrier in Memcached. We collect time consumptions in crossing a PMthreads barrier, which means the longest duration a thread might be blocked for enforcing a global Quiescent point to occur. As we would say in the results, with increased number of worker threads, there will be rising average delays in reaching a Quiescent state. And this is expected behaviors when barriers involve more threads. Okay, next I will talk a little bit about our recovery test. We evaluate the recovery process through running an insert-only workload to the data structures we use in a thread test for a fixed time, and then we force the program to abort its execution. And we collect how many insertions were issued before the crash and how many of them can be recovered after the crash. Here, the data loss denotes the elements that were buffered in DRAM and failed to reach persistent memory before the crash. Data loss is specific to PMthreads because PMthreads persist buffered content at timed intervals, whereas Atlas presents zero data loss here. Consider the recovery test over bit plus tree, we observe up to 22.3% data loss in PMthreads, with the time interval configured as 500 milliseconds. While for PM10 and PM100, the data loss are less than 2%. Okay, in conclusion, I summarize two insights you may take away from this talk. The first one is a new dual copy scheme to perform in-place persistent writes over one copy and to obtain a consistent fallback using the other copy. The second one is applying periodical persistence to general applications can obtain substantial performance gains. Okay, that's all. Thank you.